All right. Sorry, just kind of breaking up the stream a little bit. Make it a little more digestible chunks. So we're going to start digging into some code. Um, let's see. I'm going to open up our original font. So it's kind of unfortunate, but our first character is a space. So basically it's going to be all background color. That might be a benefit here. We'll see. So at the same time, I'm going to point out that this is an 8 by 8 pixel 8 by 8 font at 1 bpp, and that means that this whole character takes up 64 bits, literally 8 bytes, and we're going to use that to our advantage here. So basically this means that we can do let's see. So hold on. First thing I'm going to do is I'm going to copy this over, and I'm going to rework it here. Because when I'm here, font destination, and this will just make it a little bit easier to visualize and won't have to flip back and forth to see what's what. All right. So, first thing we're going to do is LD, which is to load a double or a 64-bit value. We're going to load that into T0, and it's going to be at offset 00 from I really like to use my numbers sequentially, so I'm going to say LIT0 pixel 8 start. And so here we're going to read from the first position, 8 bytes, and we're going to load that into the T1 register. And so let's see. Okay. We have our font. It's a whole pile of bits. The question is, how are we going to work it? So I'm going to kind of pseudocode here for a moment. We have 64 zeros. And I'm going to do this. So this is what one character could look like if only the top 2 bits were set. And so we kind of need to look at each bit and figure out if it's a forecolor or a back color, whether it's a 1 or a 0. That's all we need to know. Well, in a higher level language, we would probably look at it from here and say if 0x And then we can AND it with a mask of just a 0, 1. And look at the far right bit over here. And so here, and we can say, is it equal to 1? And I like to use the parens to make my code a little extra clear here. And so if it was equal to 1, we could assign a color, actually assign for color, else assign back color. Now, in assembly language, this has got a few more instructions of overhead. And we're going to be executing this loop, and it's a really small loop, a lot. So this is one of those times when if you really, really know your data, you can do some really cool things. And this is where you can kind of get into that, hand optimized assembly language is better than a compiled language. It's not very often, but once again, if you really know your values. So what I mean by that is, instead of this somewhat complex line, where we have our initial value, actually this here, to be fair, it's technically T1, and it was 0, test it for 1. But one of the things is we can literally say if T1 is less than 0. And that's kind of crazy to simplify this line. And it's not a complicated line. But what this does for us instead is it has us looking at this end of the string. Because the binary representation for a negative number has the uppermost bit set on. And that's what we're counting on. So here, let's see, clear. This was, and this is also part of the sign extension functionality in the register. So if I make up this number and then I tell the calculator or the computer that it's negative, watch what happens. Its sign extends it. And so again, we're just looking at that top bit, but it went ahead and sign extended the whole value. And so now it's very easy to just say, is it less than 0? And all that's going to do, especially in assembly language, is it's literally just going to look at that top bit. That's it. And then we will do binary shift to the left, and then we'll look at the next bit. So let's write some code. So here, BLE, branch if less than 0, T1, and I'm going to call it set back color. No, actually it's going to be set for color. And we'll see this, and if I made a mistake, we'll get to it here. Now again, always insert the nops first, and we can come back and see if we can optimize something. And so Now this branch instruction, a lot of branch instructions actually require two registers to compare, but this one is already saying is it less than or equal to 0. So we don't have to specify R0 or something else like that. So now we have our label for set 4 color, and I'm actually pixel 8 set 4 color and an underscore. This is not going to be this label is only for this function, and I don't expect it to be used called from outside. So that's why the prefix with the underscore. But just in case there's some other function we create that's setting a 4 color, we'll make this one the font specific version. So if we're going to set the 4 color, we can do a store half. Remember, we're doing a 16-bit color. And so we're going to store a half, and this is our 4 color, which is an A1. And we're going to store it in the 0 offset of A0 register, which is our font destination. Okay. So we actually need to do very similar. We're going to take this. So this is kind of doing branching in assembly language is kind of like doing you write the else condition and it goes and executes the else. So here, so if T1 is less than or equal to 0, that means that the uppermost bit is a 1, and so it's going to set the 4 color. So we're going to jump down, and we're going to set A1, which is our 4 color, into A0, our font destination. If T1 is greater than 0, we will set our back color here. And again, the store half is because it's a 16-bit value. 4 hex characters is a 16-bit value. Okay. So, with all that being said, I'm going to remove this here and even that. I'm going to move this up to here because that's where it would be helpful. And here, we need to skip this. So we have to be careful because if T1 is greater than 0, it will execute this line. But right now it will actually also execute this line. And that's the bad part. So we've also got our delay slot. We've got this stuff going on. And it's kind of confusing, but it's going to be much simpler code if I do this. So BLEZ is branch if less than or equal to 0, like I said. But there's this likely version. And so I just put a little lowercase l at the end of the instruction. And this is an interesting one because it now makes the delay slot conditional. It's such a cool feature. And here, real quickly, if T1 is less than 0, in a lot of cases we would set color, else set here So we'd have a one-liner on each of the if conditions, or each side of the if statement here. And that's really where we're at. And the likely instruction actually gives us this. So if the set for color is true, we can put this into there. And then actually, I'm going to say, yeah, like I said, this is going to get confusing before it gets simple. Sorry to say that. Continue. Yeah. So, once again, reading through this code, just trying to make it clear here. So, T1 is if T1 is less than or equal to 0. Oh, actually, I better look that up. I'm sorry. Spend a lot of time in this data sheet. The helps of the instructions are all alphabetical, but getting to chapter 16 quickly is second nature at this point. So what I'm looking for is a branch if less than or equal. Here is greater than or equal to, greater than 0, greater than 0 likely, on less than or equal to 0, less than or equal to 0 likely. Now we really only want less than 0. There we go. BLTZ. Branch on less than 0 and link. No, we don't want link. We want likely. Oh. Branch on less than 0 and link likely. So the link means that it's going to return to this location. So it's going to modify the RA register. The likely is the part that we want. Branch on less than 0 likely. So the instruction does exist. That is the behavior that we want. Real quick, we can look at this format and see that there's only one register that's being prompted for, and then the offset or label that it's going to jump to. We don't usually concern ourselves with the actual binary format of the instruction. BLTZL. BLTZL. All right, that's our instruction. So let's see. So if T1 is less than 0, which means that it's set to a 1, it will execute this line of code and then this line. So we don't want that to happen. BG. trying to avoid this, but I'm just going to do it. Oh, no. Okay. That is right. Sorry, this is even still a little confusing to write. If T1 is less than 0, that means that it has a 1 in the bit. Then execute this line and branch to this instruction. If this is the highest bit is equal to 0, skip this line, execute this line. So that is correct, and that 3 instructions replaces this 4-line if condition. And that is a very nice tight loop, a nice if condition. We don't have any looping yet. Still need to get that part. Okay, so we have now written out 1 bit of color. So we still have our pixel start. All right, so now we need to hold on. There, we read loaded character, font character. Okay, so these 3 instructions with the label need to be executed 64 times in a loop in order to cover every bit in our pixel. This has been really confusing. I see I got a couple of viewers. Any questions? Is my confusion being communicated clearly? All right. Well, thank you for listening. So again, the easiest way to manage a loop is to think in the do while sense. So I'm going to and I am going to, how do I want to do this? T1, R1, 64. And then while T1 is not equal to R1, do that, and add I T1 minus 1. Okay, so that should give us a single character written to our output. And this is a good time to test it. So let's see if we compile. We do, which is great. And let's debug. So we set up our automatic breakpoints and we hit the top of our code here, which is great. And remember, we've got our initialize code as the first 3 instructions. After that, we do our video initialize. And here's our not break. So this is where our code really starts here. Right there are 3 nops, and this is going to be our function. So just like I said here, we've got 4 instructions. And if we look closely, we see the LUI, ORI, ORI, JAL, another ORI. And then we follow it up with the same 4 again with the jump and link in the middle. And so we're clearly copying just those lines of code. And this is our eternal loop, which is back at the bottom here, which means that the code after this is where we're going to end up, probably. All right, so I set the breakpoint on the first instruction in our macro, and I'm just going to do F5 to run. Okay, so this is our address, loading those things up. I just want to point out here, this is a jump and link, so we're actually going to do an F11 to step into this code. So, and again, it's still going to do the delay slot before it actually branches. So it's showing you exactly what's happening. And so now this is our code. So we're starting to step through this code here. And so we're going to look in the T1 register, and it's actually all zeros, but that is what we expected. So that's all of those zeros in our T1 register. And so we'll continue to step, and the highest bit was not a 0, or was a 0 and not a 1. And so we skipped this instruction and it continued on. But I remembered I made a mistake here. Because if we just continue to step, of course it'll look perfect for a space, but it's literally only going to check that uppermost bit of the T1 register, because I forgot to shift to move my value right here. I want to shift T1. Oh, hold on. That should be like T2. That was another goof. So T1 has my character in it. So T1, I'm going to shift into itself to the left 1 pixel. And again, with our zeros right now, we're not really going to see that. So we're going to exit out, make, and rerun that. Okay. Oh, that's the boot code. Again, getting to our code where it gets a whole lot more interesting. And F11 to step in. All right, so one of the things I want to do right now is I want to go into memory and remember the A0, 1, 3, 1, 2, 3, 4 zeros. This is where our font is being written out to. So we can see we've got our first pixel written out, so that looks good. And so we'll follow along, and that's not, what did I missed something here. I'm going to do a soft reset. So a soft reset is a little bit different. It saves where the breakpoints that you created. It's not quite a full reload. So T1 register. That was another bug. This should be the T2. So the add I T2, we're just trying to make a for loop basically that increments, it counts 64. And it's a little easier to read if we go ahead and count it backwards. So I initialize the value to 64. Here's where I'm subtracting from it, and here's where I do the branching. So again, that wasn't quite right, and so we're gonna exit and redo. Oops, I exited and restarted and did not reset my breakpoints. So I am going to set my breakpoint and do a soft reset. Okay, I think we're a lot closer, so I'm going to open up this memory window. A013, 1, 2, 3, 4. It'd be nice to be able to see those same time. Alright, that still didn't work like it was supposed to, so looks like I may not have saved. One of my goals was to show the errors that I make and how to fix them. I was also hoping not to make a lot of those. All right. And my increment down here, my decrement, is still not correct. Because all of these are based on T2. One of the things, I'm a very solid believer in being able to modify code and get back to debugging as quickly as possible, as tight as you can make that code test loop. That's where the real benefits are for productivity. Okay. Alright, so we are staying in that loop. That's a good thing. Let's see what our memory range looks like. And yet another error, and I know what it is. Okay. Alright, so basically I'm finally walking through all of the pixels correctly, which is great, but I am not incrementing my font destination. And so here I need to do add I, A0 to A0, and add 2, which is the size of 1 pixel. And so oops. And now we can see that we're writing all kinds of things. So I'm actually going to set a breakpoint on the return instruction. And here we can see. Reminder, we want 64 pixels. So 64 times 2 bytes per pixel is 128, and divided by 4 is 32. Yeah, that wasn't quite the numbers that I was looking for. Basically, what I'm seeing here is I have 1 pixel too many. That's really what I'm looking at. So I have 1, 2, 3, 4, 5, 6, 7, 8, and then so 8 times 1, 2 pixels per column, 8 times 8. I'm really just 1 pixel over. So it's great to find these errors early, because if I tried to do the entire font, I would be really frustrated at this point. So what I need to do is take this and make it 63. Once again, we find these little tiny programmers live on off by 1 errors. This is normal. Doesn't mean I like them, but they happen a lot. I did save, so we will debug. Oops. Well, it drew the line. That wasn't quite what I was expecting. I'm sorry, I bumped the F12 key, and that caused MAME to run, and in my virtual machine it uses up the whole CPU and doesn't like to give it up, so we have to kill it. And that's all. F5. And I'm just going to stop at my final while loop. And it went ahead and drew the line because I still had all that code in there. But I really just want to go look at the memory. Oh. Oh. Look at that. I found another bug. So what happened is we can see it's the same memory address, but it's a very different value. Now the good thing is we did fix that extra pixel error, and we are full on pixels, so that looks correct, but it's the wrong color. So this is a bug back here. Basically, the second font applied that same color to that memory range. And so we just didn't change the memory range for our second call of this. Other than that, this all looks good. So what's left here is we're only doing a single character. So now we need to load all of our other characters. And I believe there are 95. We close the ASCII table. Maybe it'll come up quick. So, let's see. 128 minus 32 is 96, but I said 95. And the reason is the delete is a non-visual character. So again, not represented in the font. So minus 1 for that. We have 95 characters in our font. So we're going to take this same kind of code and just kind of duplicate it. Now, we know we want 95, but we're going to go ahead and guess and do a 94. And we're going to use T3 for that. And then down here, we're going to say BNE T3 R0. Go up here and add I T3 T3 minus 1. And maybe, just maybe, we will get our full font. It's kind of exciting if it's that easy. Now again, this is just expanding the font from the 1 bit per pixel up to 16 bits per pixel. So we're not displaying anything on the screen quite yet. So kind of unfortunate, but interesting. So I'm going to set my breakpoint there. I think I'm going to hit it. And I did. That's great. This was the first time that it was executed. So A013, 1, 2, 3, 4. And I'm not seeing the alternate color. What isn't right? Well, let's take a little closer look. B636. B636. And that is our light steel blue. So if we come back here and we say that that is our background, which is A2. All right, that little if statement, this is not working like I expected. Because what's happening is this line is always executing. Oh. because it should. Yes, it should. Add I T0 T0 8. Because that code is working, I believe, and what is happening is we are not reading a new character, we are always reading the same character. The space, which is always zeros. So this should force it to read the next character. And remember, this is the load double, or 8 bytes, and so that is incrementing by 8 bytes. All right. Okay. Again, I think I'm just going to let that run. So we loaded up one font, A013, 1, 2, 3, 4. All right, and we were expecting a bunch of these. Oh, but we wanted a little more variety than that. Okay. I'm sorry, this video is running much longer than I intended, but I really want to get this. So let's read the code. So T3 is there, and we decrement through. T1 is our loaded font character, and we check it there. Oh, wait a minute. Oh. Okay. A0 is the font destination, and the bit shifting there. Wow. Okay, that was kind of... Yeah, so kind of what was happening is that these two lines of code had kind of become conditional based on the high or the low bit. So also, if you look at this memory thing, this memory view, we kind of end in a funny place, not where we would think. Here's another test that we should be doing. We have 95 characters. Oh, okay. There's a little bit more math than I just wanted to knock out on a calculator. So, 95 characters, 64 4 pixels per character times 2 bytes per pixel. Okay, so that is how big the font is in memory when we expand it up to 16 bits. I'm going to flip this over to the hex value, and not that that value directly means anything, but watch this. 2F80. So if we take our value here, well, that's a really easy value because the last set is zeros. So that means that our last pixel should be within a couple of bytes of 2F80. And when we come back here, it is not even close. Should be much larger. Okay. So that's still all commented. But as I said, I moved that. Okay. Alright, so we're going to go look at our memory. A013, 1, 2, 3, 4. Hey! Right here we have some variation. That's the good sign. I think we've got it right. So that is very cool. And just to glance, take a look at the same thing up at the second memory range. And again, lots of variation. And let's see if it goes to the 2F80 that we predicted. There we are. Perfect. I expect that to be correct. We'll double check that last value on this range as well. F80. That is great. All right, I'm going to do one last thing just because I think it'll be fun. Thank you, very patient viewer. So at first we attempted to dodge the frame buffer itself, but instead let's use it. And now this is going to be interesting because it is not, I repeat, not going to show us our font like we would think. We still have another step before we can start drawing characters on the screen. But it will show us something interesting on the screen. A little more variation. Hopefully just a little more interesting. All right. And there it is. So that is what our font kind of looks like in memory. Kind of wild. I don't know if it's quite what anybody was expecting, but to explain why this makes sense is each of our characters is laid out in memory, as 64 pixels in a row, not in a square. So there is a line here somewhere that is 64 pixels long. And just actually based on these dimensions, I would say that that line starts in the upper left and probably goes to about there. Those white that white space is rather interesting. I'm not sure if I can explain that. I'm not positive. Oh, but you know what? We can go slow. Uh, okay. Okay. So this is our next character condition. So I'm going to set a breakpoint on that. And yep, I was approximately correct. So I'm betting that, well, I don't know. Well, let's take a look at the next character. Again, I got the breakpoint in the right place, so I'm just going to hit F5. And we draw it across the top. One character at a time. So I'm going to call this video done. Our next step is going to be to take those 64 pixels in a row and put them into 8 rows of 8 pixels in order to draw an actual character. And we'll start playing with a little bit more with ASCII. Once again, did not expect it to go quite so long, but I'm really happy with the current state. So thanks for hanging out.